Why doesn't a rocket just go straight up to get to space? It sounds like it should. Point it upward, fire the engines, and you're there. But that's not how spaceflight works. Because getting to space isn't about height, it's about speed. Speed high enough that as you fall back toward Earth, the ground curves away beneath you. That's what orbit really is. So let's launch a space shuttle and see how it actually gets there. This is Earth. And this small vehicle sitting on the surface is about to attempt something extremely precise. The space shuttle isn't just trying to reach space, it's trying to stay there. At liftoff, the shuttle ignites its main engines along with two solid rocket boosters. For the first couple of minutes, it's pure thrust, pushing straight up through the atmosphere, fighting against gravity and air resistance. It's loud, it's violent, and it's necessary. But almost immediately, the shuttle begins to tilt. This maneuver, known as a gravity turn, is where the mission starts to shift from brute force to precision. Because the goal is no longer to go up. It's to go sideways. To remain in orbit around Earth, a spacecraft needs to reach a speed of about 7.8 kilometers per second, over 17,000 miles per hour. So instead of continuing straight upward, the shuttle gradually pitches over, building horizontal velocity while still climbing. By the time the solid rocket boosters separate, the shuttle is already traveling at extreme speeds across the surface of the Earth. The boosters fall away, their job complete, while the main engines continue accelerating the vehicle forward. The rocket boosters fall back to Earth and land softly in the ocean to be reused later in another flight. About 8.5 minutes after launch, the shuttle reaches the speed required for orbit. At that point, something counterintuitive happens. It stops going up. Instead, it begins to fall. But it never reaches the ground, because it's moving forward fast enough that as it falls toward Earth, the planet curves away beneath it. This continuous freefall, combined with high horizontal speed, is what creates orbit. This equation tells us how fast we need to go to stay in orbit. It depends on how massive Earth is and how far away we are. The closer you are, the faster you have to move to avoid falling back down. The shuttle is now in low Earth orbit, roughly 400 kilometers above the surface, circling the planet every 90 minutes. Inside, everything appears weightless, not because gravity has disappeared, but because both the shuttle and everything inside it are falling together. Reaching orbit, however, is only part of the mission. Returning to Earth requires just as much precision. To begin the journey home, the shuttle performs a small burn in the opposite direction of its motion. This reduces its speed, lowering its orbit, and allowing gravity to pull it back into the atmosphere. From this point on, the descent is unavoidable. As the shuttle re-enters the atmosphere, it encounters air moving at hypersonic speeds. The air cannot move out of the way quickly enough, so it compresses and heats to temperatures exceeding 1,500 degrees Celsius. This creates a layer of plasma around the vehicle, temporarily disrupting communications. Despite these extreme conditions, the shuttle is carefully guided through re-entry, using its shape and thermal protection system to manage the intense heat and forces. And then, in the final phase, something remarkable happens. The engines are no longer in use. There is no thrust. The shuttle becomes a glider. It has one chance to line up with the runway, one opportunity to land. There are no second attempts. After traveling thousands of kilometers, orbiting Earth at incredible speeds, and surviving the heat of re-entry, it returns to the ground as an unpowered aircraft. From launch to orbit to landing, every phase depends on precision, timing, and a deep understanding of motion. Because in spaceflight, the objective isn't to rise above Earth. It's to move fast enough to keep falling around it. And maybe that's what makes it so remarkable. The Space Shuttle wasn't just a vehicle, it was a system built on ideas that demanded precision, trust, and an understanding of physics that few technologies ever require. In many ways, it felt ahead of its time, pushing the limits of what was possible, not just in engineering, but in how we thought about reaching space and returning safely. And even now, long after its final flight, it stands as a reminder of what can be achieved when we don't just fight the laws of nature, but learn to work with them. Thank you for watching. If you enjoyed this video, please like, subscribe, and comment down below with ideas of what you'd like to learn about.